Welcome to Lab 4 in Compute 127. And this lab is going to be more practice. We're going to work with Makefiles and sort of exercise some of the concepts that you've learned already, just to make sure that things are sticking in your brain. So what we're going to start with is setup, and the setup is quite easy in this case. So as you can see, the setup section is quite small. Let's start in your Git repository for Compute 127. And as you can see, I'm assuming that you've gone through and done lab 0, 1, 2, and 3. So there's a bunch of files from lab 3, and in lab 4 we're actually going to use some of those files as helper functions to help us solve slightly more complex things in lab 4. So the first thing we'll do is make a directory called 4. We're going to add it to our Git repository. We're going to go to 4, and I would recommend at this point copying over a few files that are going to be useful to you. So draw.c and draw.h, I'm copying from the 3 directory into the 4 directory, and I'm going to copy 3 image pos.c and image pos.h. Image ops.c and image ops.h into the current directory. We also would like to get the Makefile. We also need the PNG files. And finally, we want a function, a file that has a main function in it. So I'm going to copy the test.c in here. And since I've copied all of these files here, I can try to run a make and see if it works. And it seems to work, and I run test, and it should launch a black image just as before. So everything is now set up to, you should add all of these files to your Git repository. You add the Makefile and all of the other files. So star just stands for, it's a wildcard. Star just stands for any file. So any character sequence is matched by star. So if I do a git status, at this point, it shows me that I've added a bunch of new files here. Okay, now you're set up with all the files that you have copied over from assignment or lab 3. Now we want to add our new functions based on the requirements of lab 4. So if you look at the first task is to write this function called drawCircle, and we want to add a single C source file called t1.c, which contains the definition of drawCircle. It should at least have this one function in it. It should definitely not have any testing code in it, so no main function should be in t1.c. You can have other helper functions. You can have as many functions as you like to help you solve this task, but you should not have a main function or any testing code functions inside this file. So instead, let me show you how we can test this function drawCircle by using the commands and the commands like make, and also the Makefile that was given to you in lab 3, and the other helper files that you received in lab 3. So if I go here, you can see that I've created a file called t1.c. It contains my solution for drawCircle. Now I want to test this, so I want to add the drawCircle function call to test.c. So I'm going to use nano just to make it using editor that you can use yourself and follow along. And you can see that it test.c includes header files like draw.h which is in the current directory png.h for loading PNG files, and image manipulation functions. And these image manipulation functions, you have to use the ones that you wrote in lab 3, and they're going to be helpful for you in this lab. So in order to test out draw circle, instead of a window width of 400 by 400, I'm going to do a slightly smaller window size of 160 by 160. And instead of dividing this by 4, I'm going to just replace it with a small image size of 16 by 16. So you can see what this does is it just creates a 16 by 16 image, but each pixel is going to be quite big and easy to see. And that's the goal of having the window width be some multiple of the actual image width in terms of pixels. That's the only reason, really. And so now we go down here. This is the test.c from the previous lab. So we're going to just create a new comment here that says this is a good place to test the tasks from lab 4. And what do I want is to call draw circle. So let me go back to the web page here. We know that your definition of draw circle has to follow this this function declaration. So what I'm going to do is tell the testing function what function it has to know what kind of function it's going to call. So it needs a function declaration before it can call it. So I'm going to copy that. I'm going to go back and I'm going to paste it into my test.c file, which contains the main function. So notice that I have told test.c that there is a function declaration for draw circle. Now you can also just have a header file that contains these function declarations, and that's equivalent to putting it in here. And let's now add a call to draw circle, and let's go back to the web page, and you can see here's an example that's it's using a 16 by 16 image, and it's drawing a circle in it, and it's a trivial one, but let's just start with that. So I'm going to copy it into my test.c, and that's going to call the draw circle on this image, and there's a comma that's missing there that needs to be added in, and I'll control X to exit, and I will say yes to save the changes, and test.c is the file name to write. Now what we have is in test.c is a main function that calls draw circle, but t1.c did not exist in lab 3. So if I look at the Makefile that tries to compile test, so you can see here it's trying to compile test, and it's going to compile all of these C programs, and it's also in it's going to create a binary called test by compiling all of these C programs. Well, it doesn't yet know about t1.c, so we're going to add t1.c in here, so that when I run make, so what make will do is it'll look for the first rule. This is the rule, starts with a colon and a name, and so it's going to try to create this test file, which is created by this compile instruction here, and it's going to compile all of these source files because that's assigned to source 1, and this variable is used inside this rule. So it says if any of these files change, or if you edit any of these files, it will run this command, and what it's going to do is, you can see the same variable is used here, source 1, source 1. So it's going to compile all of these C programs with appropriate flags, C flags, so that all of the commands to include the X11 windowing library and all of the other things you need like libpng, all of that are stored in C flags and LD flags. And so now I'll save this Makefile. So I've edited the Makefile. Just be careful when you edit the Makefile that you don't change this part here. This is supposed to be a tab character. So when you, if you can see here, that's one character. That's a tab. If you try to go left from the CC and you see a lot of spaces, that means somehow you've ruined the Makefile. It has to be an exactly one character, which is a tab character here. Otherwise, the Makefile doesn't work. It's the only really negative thing about Makefile is that it's very finicky about this particular property of the Makefile. It has to be a tab. So I'm going to get out by pressing Ctrl X, save the changes, and save it to the Makefile. And now when I run make, it's going to compile all of these C files, and it's going to, when I run test, it's going to show me the result that I expect, that I can compare to the web page. So that's a way of testing your code. You can go further and create the second test, which is for, and the web page is this series of circles. So the way to test that is to load up the test file, and this time I want the width to be a little bit bigger, because this window is going to be a little bit bigger. So I'm going to go and change this 160 to be 640 as the width and 320 as the height. And I'm going to create an image which is 64 by 32. Again, this is so that each pixel is nice and big and visible. And now I can go down, and instead of testing the first task, I'm going to comment this out, and I'm going to go back to the web page and copy and paste the testing code that's written there. So it says for these values of I from 10 to 1, it's going to run a draw circle command, and so I can save this now in the usual way. And again, I'm going to do a make, and I test, and you can see that the output here matches what I expect to see for this particular test case. Okay, so let's step away from the details of the different tasks in Lab 4 for a second, or a few minutes, and look at a example piece of code that is in front of you here. And the main goal of this little section of this video lecture is to emphasize the use of asserts to check for cases where you might get incorrect data as input to your function, and you want to always check whether your assumptions about the data are true or not. And we often use the assert statement to make sure that we make our assumptions about the data explicit in the source code. So let's look at this code. Let's start from the definition of main. So that's line 14. And we go down and it says, okay, there's a unsigned integer length, and len is assigned to a value 1000. And then what we do is we allocate using malloc a 1000 size array of characters in the heap memory, and we get a pointer to that heap memory, which we assign to this variable called array. And then the first thing we do is we go through each element from 0 to less than len. so from 0 to 999, and we go through and we assign to each element of the array a random number, and we make sure the random number is always going to be between 0 and 255 using the mod function, the mod operator rather. And so I would encourage you to look up the mod operator if you don't know what it does. Now the next step is to deliberately create an index that is going to be legal. So this is 1001, which is beyond the end of the array. And then it calls a printf statement with the index and the value of the array at that index. And so instead of just using, so you could have used at this point array of index, right? And you don't need to use safe index. So this is an unsafe way of doing it. Just assume that whatever index you get is going to have a value. But this is dangerous, as you can see that this index may be beyond the length of the array, and so we should probably check that. So that's why it's doing it this way. We call safe index, and let's look at the definition of safe index over here. It takes an array, it takes the length of the array, len, and an index, and then it makes a few assert statements. So you can see the assert statements in line 7, 8, and 9. And the first assert statement says array is not equal to null. So if array is null, the malloc failed and gave you a null, basically a 0. So null and 0 are the same thing in C. So null is just a variable that's defined to be 0 because we want to kind of say that it's a null pointer rather than an integer value of 0. So it allows you to distinguish between pointers that are null and just values that are 0. So it's just a convenience factor. And so this one says array is not equal to null, so there is something in the array. And then we check whether the index is less than the length of the array. And we also want to check that the length is not negative or something crazy, so we don't go and try, there should not be a thing as a negative length array. So we say that the length should be greater than 0. And the order of these assert statements may matter or may not matter. So you should think about that, whether the order matters. It's just saying each of these statements has to be true. So array has to be not null, index has to be less than length, len has to be greater than 0. These three facts about the input variables should be true. Only then will it go past line 9, go to line 11 and return the index, the value of the array at that index. Now if you look at this program, there's something wrong with it. So if you look at this, there is an assert that you could have done that's missing. So I encourage you to pause the video at this point and take a look at what you think is an assert statement that should be in this code that is missing. One of the new concepts I want to introduce to you is the concept of a multi-dimensional array. So we saw last time in lab 3 specifically that you can represent a two-dimensional piece of information like an image in a single dimensional array. But C also has multi-dimensional arrays, and I just wanted to take this chance to expose you to the syntax of a multi-dimensional array. So here's an example of a multi-dimensional array that's two-dimensional. In this case you have the number of rows, which is not specified in the type declaration. The number of columns is specified, and this number 4, which is the number of columns, has to be specified. You cannot leave it out. You can leave the number of rows out because it can infer that, but it cannot infer the number of columns. And that's just a sort of a restriction by the C compiler. There's no special reason why this is true. It's just a fact, and you have to deal with it. And here in this array, I've allocated it statically. What that means is I am giving this array an initial value that's specified using this syntax, which includes brackets. So this entire declaration here is declaring a two-dimensional array, and it has 5 rows and 4 columns. And in this comment, each of these comments shows you this is row 0, row 1, row 2, row 3, row 4. So that's 5 rows, and then this comment here shows you that the first column, column 0 is all 1s, the second column, column 1, the index is column 1, is all 2s, all 3s is column 3 or index 2, and then the last column is column 4, which is index 3. So these 4 columns, you can initialize an array using this representation, and the rest of this program, all it does is simply print out the two-dimensional array, and you can see that in this variable I is going through each of the rows, this variable j is going through all of the columns, and it's printing out each, it's going through each of the values of the columns and printing them out here, and then after that row is done, it prints a new line. And so if I run this program, I can do cc 2darray.c, and I run it. You can see that it prints out the contents of this two-dimensional array. And now just let's take a quick look at how to generalize from 2 dimensions to multi-dimensional arrays. So here's an example of a 3D array, and the dimension is 3 times 5 times 4. So as before, the first dimension can be left out, but the other 2 dimensions, the 5 and the 4, have to be specified. So you can see here this part looks exactly like how we defined a 2-dimensional array before, except that's now the first element of this array that's starting over here. So you can see that there is a open parenthesis, close parenthesis that defines the first element, and there's a comma, and then the next element starts here. So there is, this is the first element. The first element itself is a 2-dimensional array, and that two-dimensional array has the number of rows is 5, the number of columns is 4. So it's a 5 by 4 array. And then the next one is again a 5 by 4 array, and they have to be exactly the same dimensions, otherwise it just doesn't work. And then finally there's another element here, that's the third element that's also. So basically this array that I'm defining has 3 elements. Each element is a 2-dimensional array. And there are 3 two-dimensional arrays, and if you look and zoom in into one of these, that is an array which has 5 elements, and each element in this array has 4 columns, right? So there's 5 rows, 4 columns. And that's how you define a multi-dimensional array. And we have to have 3 indices, I, j, and k, because it's 3-dimensional, and I can print I, j, k, and then at the end of each row I print a new line, and then the end of each 2-dimensional array I print a new line, so that I can keep each component of this 3D array sort of separated in the printer when I print it out. And so when I run this 3D array and I run it, you can see that it produces the desired output. I have the first 2-dimensional array, the second 2-dimensional array, and the third 2-dimensional array from my static initialization of this 3D array. Okay, so just to finish off this video lecture for Lab 4, I wanted to go back to the question I asked earlier about what was wrong about this program and what was the condition that it was not checking. And one of the things, so hopefully you found the answer to be quite obvious. So when we do a malloc, we should always check whether the result of the malloc, this malloc is going to ask the operating system to give us some memory on the heap, and it gives us a pointer back to it. We want to check if this is a valid pointer, and if there was in fact memory available for us to use. And in this case, it's actually just going ahead and assigning stuff to array I without checking if array in fact was pointing to something legal. So if it's pointing to something illegal, it would be a null pointer, whereas basically the return value of malloc would be 0. It would be a 0 pointer which doesn't point to anything. So what we want is to say assert that array is not equal to null. That's what we want to assert here. And if in fact for some reason malloc failed, then our program wouldn't then continue. It would give a good error message which says that, hey, malloc didn't work, you should go and buy more memory, or something else went wrong. It wouldn't just go ahead and assign random stuff to memory location it doesn't own. Because when you do this, it's not guaranteed to segment, to give you a segmentation fault. It's probably likely that it will, but it's not guaranteed by the C compiler that it will check unlicensed sort of memory accesses. So in order to avoid bugs in your program, you should always use assert in order to check for these properties. And now, so this is still a bug because it's an index that's greater than the length, so I can remove that. And now I can run this program, and at the end I should always free the memory location that you malloced. So you should always get rid of the memory that you allocated so that it can be reused by other parts of your program. If you don't, it's a situation that is often called a memory leak. So now if we compile assert.c, you can see that the character at this position is some random character, but everything worked, all the assertions worked, and it gave us the right answer.